Hey guys, what's up? Today we're gonna go over kinematics from AP Physics C. I don't know why I blanked on that. Hope you guys enjoy it. I'm gonna just be going through this, and I'm probably gonna go through the other chapters as well. So kinematics is the object's motion, okay, and then in the next chapter we'll do dynamics. So position is relative to a coordinate system, and distance is scalar, and displacement is a change in position. So change of position equals displacement. The distance is total amount traveled. So how are these two different terms? Displacement. There is no displacement change if an object went from here all the way back to itself. However, the change in distance is changed. So there will be some value x, but change in displacement will equal 0 since it arrived at the same place. So it's actually denoted as change of s, where it means spatial location. P is not used for position because it's reserved for momentum. Then change of x is the change in distance, or change in position. Okay, that makes sense. We can do this example. Traveling along, it starts from 10 meters from the origin, then moves 8 meters away, and turns around and 12 meters back. So you add that, 28 minus 12, final position of the car, the distance the car traveled, and the displacement of the car. So final position will be equal to the total displacement plus 10, but we have 28 minus 12, and 16 is the position, if that is correct. Oops, no, I can't do math. Sorry, guys. Should be 6. Right, because it goes up 10. So that's reaching the 18 point going back. So this will be 6. Change in displacement is 4, since 10 is, this would be negative 4 in specific. And then distance, or change in x, have to be 12 plus 8, so 20. Don't forget your units on the other takeoff points. In front calls this, and this, we don't have to do all this. Basically, you can just make a triangle and do some stuff. Okay. This one is a round oval track. We can do this one. An athlete runs once, total distance, find the displacement is 0 because he started and finished in the same place. Okay, easy, like I was talking about before. Speed and velocity is this, okay? When we're moving in a car, speedometer tells us how fast we're going, gives us our speed. But what does it mean to have a speed of 10? We're covering a distance of 10 meters every second. By definition, average speed is the ratio of the total distance traveled by the time required to cover that distance. The speedometer doesn't care what direction, as long as the wheels are moving forward or backward. You could be drawing this. Okay, speed is scalar. Direction, to make it velocity. So velocity is the change in displacement over change of time. The bar over v means average because s is a vector. This is also a vector. But the change in direction, or the change in x, which is change in position or change in distance, is actually just a scalar. That's what makes it different. Okay, note the distinction between speed and velocity. In everyday language, they're used interchangeably, but in physics, speed and velocity are technical terms. Speed is defined by the total distance divided by the elapsed time. On the other hand, magnitude of average velocity is the vector displacement divided by the elapsed time. However, the car speedometer is not telling you the average speed over how long, it's supposed to tell the current speed, and we do that with changing the change to a d, as in the derivative in in calculus. So we have an instantaneous rate of displacement times the change in time, or that instantaneous moment in time dt. So we know that we can find ds by simplifying, by breaking this into I forgot what differential equation and taking the integral of both sides. So you can simply just have vt equals s, or s is equal to dt. I forgot. I thought you could do that. Look, you forgot calc. It's been a minute. I took multi last semester, guys, and it's senior year, so chillax on me. Often our derivative in respect to time is denoted by the dot above the quantity. So an alternative notation equation is this. Interesting. That's actually very interesting. I didn't know that. Probably won't use that, but maybe we will. Okay, since the magnitude of the display... Okay, let's do magnitude of his average velocity. So let's go back to this infant question. In 20 seconds, it crawls 5 miles east, 3 miles north, and then 1 meter east. Find the magnitude. So we know the magnitude is going to be this. We know that 8 is... We know that 6 is in this direction. 3 is in this direction. Therefore, using Pythagorean theorem, square root of 45. Okay, going back over here. Since we know that this is square root of 45, we can use this. Find the magnitude of the average velocity. We know average velocity is equal to the collapsing of time over the total distance. Or let's just double check that. I don't remember. It was total difference. Total displacement. And in this case, it's the same. Displacement was this, however, distance was that, right? Does that make sense? Distance was a 3, or the different parts that he had. Well, displacement was the whole thing, and then we divide that by 20. Boom, we get this, okay? Assume the runner in example 3 completes the race in 1 minute 18 seconds. Find her average speed and the magnitude of her average velocity. Average velocity, we know, over the whole time is going to be 0, correct? Because it's the change of displacement over change of time, but this is already 0. Therefore, the whole thing is going to be 0. Okay, average speed, on the other hand, 400 meters over how many seconds? 78? Whatever that is. There's 5.1, they say. Then, okay, just remember the v-bar. This is average. Is it possible to move with constant speed but not constant velocity? Let's just think about it for a second, what it means to be. So constant speed means cruising. I mean, the change of acceleration, the derivative of acceleration is equal to 0. That makes sense. So, this is actually correct. Because if we think about it, although both of these will satisfy this direction, the speed could change. However, in terms of acceleration, I believe for centripetal force, it could be an object going around, where the velocity is changing instantaneously every time. Speed is still staying the same. And I believe there will be a constant acceleration, but I low-key forgot. I think actually acceleration is equal to 0. We're looking for that. It's possible to move with constant velocity, but not constant speed. That, however, is incorrect. No, second statement is not incorrect. Because if there's constant velocity, the magnitude of a constant velocity equal to the constant velocity speed, which will be always true. So this is no. No, yes. Okay, an object's position x obeys the equation this. Where t is time in seconds since the object began moving, how is it moving at this? Okay, so we know that object's moving at this. To find the time at which object's motion, this is basically calculus, right? We'll have to take the derivative to find the change in x, the instantaneous change in x at that time. So the derivative of x dt is equal to, I believe it's like, I look, forgot notation, but I think it's this sine d dt t. So then we can make this cosine, right? Cosine t dt. I think at the end, I don't know. Actually, we keep this, but x d dt. You can plug in pi over 2. If you know at pi over 2. This is pi over 2, this is pi, right? Cosine is equal to 0. Therefore, how fast is it moving? It's moving 0 meters per second. Okay, good. So just you have to say this is equal to velocity. So we have to put the instantaneous velocity. It's automatically assumed, okay? Boom, now we're talking acceleration. When you step on the gas pedal, your speed increases. Step on the brakes, the car decreases. Turn the wheel, etc. Motion changes, velocity changes. Describe the changes in velocity. We need a new term, acceleration. In the same way that velocity measures a rate of change in an object's position, acceleration measures the rate of change in the object's velocity. Does that make sense? Yes. An object's average velocity, or average acceleration, is done as below. Boom, a bar. This is the simplest equation you can kind of see. Change in v over change of t. The units of acceleration are meters per second, because we take the change of v, and then, which is change of x over change of t, take v bar, and then we just divide that by change of t, which is squared. Okay, a is also a vector because t is a positive scalar direction, is the same direction of v. That makes sense. So, a and v will be scalar multiples of each other. So, they will be parallel vectors, I think. No, they won't. No, they don't gotta, because the change of that vector is actually a really interesting point. I actually disagree with this because change of acceleration could go in this direction. Velocity could be going in this direction. Oh. Yeah. Change of v, that's the difference. They're not saying velocity and acceleration are parallel. They're saying change of v is parallel. So you know change of v is equal to dx dt, and also velocity final minus velocity initial. And because of that, acceleration is equal to change of v over change of t. So using this information, we're going to be in the same direction. Furthermore, if we take our object's original direction of the motion to positive, and then an increase in speed corresponds to positive acceleration, while a decrease in speed corresponds to a negative acceleration, deceleration. Note that an object can accelerate even if the speed doesn't change. That is very interesting when we think about that. The speed doesn't change. Speed remains constant. Only way that's possible is assuming that the object is in circular motion, where acceleration is towards the middle. Speed is not changing. However, the velocity vector is changing over and over. Again, it's a matter of not allowing everyday usage for accelerate to interfere with technical physics usage, because acceleration depends on change of v and the velocity change. If speed changes, direction changes, both speed and direction changes. Just a transition from average velocity to instantaneous is doing the same thing. Since velocity itself is a derivative of position, it implies that acceleration is the second derivative to the position. If that makes sense, that should make sense. In dot notation, we say that a is equal to this, which is equal to this. Okay, and this is simple again. Right, we just differentiate, and it should give us this. Okay. And that is just another cheat sheet for you if you want it. I think I'm pretty chill though. Okay, a car is traveling a straight line along a highway, constant speed of 80 miles per hour for 10 seconds. Find its acceleration. Okay. So, I think the thing that's here is constant speed. So again, acceleration is equal to change in velocity or change of time. We see that velocity is equal to 80 at the final and 80 at the initial. So this is 0. So unfortunately it's not 8, but it is actually 0. So a car is traveling along a straight highway, speed 20 miles per hour, meters per second. It steps on the gas pedal, and 3 seconds later it is at... Oh, sorry, I thought it was the brake pedal. And I was so confused because it's like the car is traveling backwards. Okay, so we know that average acceleration, change of velocity over change of time. We see the change in being 12 over 3, which is equal to 4 meters per second, being average acceleration. Okay, boom. Spotting a police car ahead, and previous slows from 32 to 20. So this is a -6. Right. Meters per second, I think. Okay, one thing I messed up. Units are very important. Don't forget, don't mess up your units. It's really easy to lose points on that. Okay, it should be meters squared. Position of the object measured in meters from the origin is x equals 0. Moving along a straight line given as the function of time t. By the equation, this find velocity at time t, acceleration at time t. Okay, so velocity at time t. We might look at this and go, whoa, but chill, it's not that bad. Okay, we know the velocity is the first derivative. Taking the first derivative of this, it's just 8t minus 6. The second derivative is just 8. Time at which it's the origin. It would be when when the whole equation equals 0. We can try to... Look, we forgot how to do this with derivatives. But since we know the two factors, I think if you use those, times get 40. Yeah, wait. Do you use those? I'm not sure actually. But time at which, I don't know what the really fast way to do it. I'll just do trial and error, like try 2, 8, no, 3, 9, 36. 36 minus 8, no, wait, what? Try 5, 100, 30, 70, no. 4, 64, 24. Yes, 4 works. 4 seconds. Then we literally just plug it in. So 8 meters per second, and then this one would be 32 minus 6, 26 meters per second. Okay, if we know, boom, boom. I think the only thing we missed was this and this. See, okay. This is really important. Oh, we just had a factor. I mean, that's pretty chill. I don't know if there's another way to solve it via that. There's probably some way to do it. Calculus, but I low-key forgot. I'm gonna like review that when I get time. The object acceleration is this. Okay. Moving along x with okay. So this is basically just looking and taking anti-differentiating these functions. So given a 6 and moving 2 meters per second, you can take the integral and find that t squared 2t squared plus 7t is equal to v of t, velocity at time t. Thus, we can also find the position, which is a little bit difficult, but actually no. We actually know we'll find the position. So at 4 seconds, we know that the object will be traveling at 16 times 2, 32 plus 28 equal to 60 meters per second. And this is some dumb number like 64. So something went wrong with my math. Oh. See, we're almost there, but we got one factor wrong. We forgot that we always have to add a c factor. Then we set it equal to 0. And t equals 0, we know that is 2. Because we add a 2 over here. And that's just my fault, guys. But this should be 62 then. And because of that, this is 2 plus c. And we know at times 0, it's at 6. We add a 6 here, t here. And then all we do is add 4, right? 8 plus 6. But I don't know what went wrong with my math. I think it's everything else is right. Right, 2, 62. And then, I don't know what I went wrong with my math. I actually don't. Oh, because you can't add those two numbers. Make them both 3s instead of 2. Really? I'm actually kind of dumb at that. But it's okay. Like, low-key, you understand we have to do some BS stuff that makes you do all this work. But thank goodness that was the last question. Oh, how much more is this chapter, bro? What? Okay, wait. I don't remember what page you were on. uniformly. This is page 126. We keep on going. Keep on going. It's 2D, bro. Keep on going. We'll do the drill too, because why not? Oh my gosh, there's full stuff. Don't even remember the question page that we were on. 6 is 162. Don't even remember where we were at. 162. Can you remember that in chat? '62. So we have 23 pages for one chapter left. Dang. I think I'm gonna take a break here, low-key. This video is getting a little long. I'll finish the next chapter in the next video.